Hey, in this video, I'm going to show you how containers work, but like for real. We're going to build our own container runtime. This is based on a talk that I gave at the Southern California Linux Expo, and I got a lot of really good feedback. This teaches some low-level stuff that really impacts how we develop. So hang around. This is gonna be cool. So what I'm going to go through is a little bit of my history and how I ended up building my own container runtime, which is going to transition into talking about Unix and Linux and where it came from. Then we'll build our own runtime. We're going to use Go. We're going to go quickly. It's not that much code. It's not that complicated, really. We'll learn some Linux stuff. And then at the end, we bring it all together and you'll kind of actually understand what containers really are. So that's kind of my goal. Peel back the layers, understand what's happening. It'll change your life. Okay, maybe it won't change your life, but it'll be interesting. I love this XKCD comic about containers because I find it so true, right? Like I run containers all the time. There's probably one running on this machine right here, right now, but I never really understood what they were. So that's what I want to talk about, right? What is a container runtime? A container image is like something you host maybe in Docker Hub or a container registry. It's like something at rest. When you start it up, it becomes a container. It's running. And the container runtime is the thing that does that start, right? That starts it up and manages it. So think of like Docker run, basically. But more specifically, there's a bunch of different container runtimes. There is runc. I'm pointing at my screen, but you can't actually see where I'm pointing. But on the left, there's runc. It's very simple, right? Containerd used by Docker, I believe, a little bit more complex, a little bit more fully featured. Then you have more complex runtimes like Firecracker and Kata containers. I'll actually run a container inside a virtual machine. None of this matters except to say that I'm going to be talking about ones that are very simple container runtime. Like we're going to build something more like runc than like containerd. But another way to think about containers is about the absurdity spectrum, right? It's not talked about very much. Containerd is a very normal, like business appropriate container runtime to use. On the other side, you have Docker, which is a full reimplementation of the Docker CLI in Bash. It's kind of an insane thing to do and kind of awesome. And if you try to read the Bash, like I think it's only a couple hundred lines, but it requires 100 dependencies that it all chains and pipes together, and I couldn't understand it at all. It's absurd and it's awesome. We're going to build something a little bit in the middle. I'm going to build chrun. It's going to be a little bit absurd. I don't recommend you use it. So this is my end goal, chrun. You can type chrun, run, Redis, and it's going to start up a Redis server, right? It's going to pull down the Redis image from Docker Hub. It's going to start it up and you can use it. And it's like it's a real runtime, sort of. So how did I get here, right? I used to have a job. I worked for a security software company called Tenable. They make the Nessus scanner. But what I worked on was container security, and it was actually more properly like image security. What we did was we would take these containers from people's registries, these OCI images, we would pull them apart and find vulnerabilities, right? That there's this package installed that has a known vulnerability, you should update it, kind of give people warnings like that. Docker CLI can actually do this itself now, I think, with Docker scan. But anyways, I had this job. It was a lot of fun to build that software. And I learned a lot about how images worked, but not a lot about what happens when you actually run a container, right? The thing I knew was kind of like this box, right? The shipping container. A container is like a shipping container. It's sort of a box and you put software in it. It's like a packaging format and you hand it off. But that's about all I knew, right? I was using containers all the time, but I didn't really know what they were. And if I tried to look into it and figure out what they are, I kind of always heard the same things, right? A container is not a VM. It's very important that you understand that because it's more lightweight. People would say like, oh, it shares user space, as if that meant something. That means nothing to me. It didn't mean anything to me at the time. But then they would say like, but it's sort of a VM, right? It's not a VM, but it's sort of like a VM. That's the best way to understand it, which didn't explain a lot, but was enough. It was enough for me to get by. But then I get my next job, which is at Earthly. And, it's early days. I'm trying to figure out how Earthly works. It's an open source build tool, right? Makes sense. And it uses containers to do build isolation, right? To separate things from each other so that builds are repeatable. Makes sense. It does this using runc, which if you recall, is like the simplest of these things. But then the back end, the Earthly actually does the building in, runs in a container itself. It runs in BuildKit. So it builds things using containers, but it's itself inside a container. I found this concept a little confusing, right? Like basically if a container is a box, then Earthly is putting boxes inside boxes and builds are getting faster because of it. That doesn't really make sense. Like putting boxes inside boxes doesn't make things faster. So this didn't make any sense to me, right? And I kind of felt that I had to lean into this and understand what was going on. And so I started looking around, kind of doing some research, trying to figure out, what containers really were as part of, just getting oriented at my new job, right? And so, I'm eating lunch one day and I'm watching YouTube videos and I find this talk by this Jerome Pedizzoni. He worked at Docker in the very early days, and he was trying to explain to everybody what it is. And the talk is fantastic. It's called cgroups, namespaces, and beyond. What are containers made from? But the thing he says in the talk is that a container feels like a VM, but it's not. It's just chroot. It's just chroot on steroids. Okay, now I have a thread to pull on. First of all, I don't know what change root is, so let's start there. So change root looks like this, right? On the left here, I have my file tree structure, and you can see the root is the very top. That slash in your path at the very top is the root of your path. And then if you run change root and I pass it this path, slash home slash arranges slash WRK in the space, and then I'm going to pass it bin bash, then it's going to transition to this one on the right side, right? It's going to take the root from being that top level thing and move it down to this new location we've given it. And since in that new location we gave it bin bash, it's going to start up bin bash inside there. And that slash at the top of bin bash is going to be relative to that new location. And inside that bash, when you look around, everything you see is going to suggest that the root ends at that new location. You're not going to be able to get back up, right? It's taking a branch of a tree and saying, this is now the root of the tree for you, for this new process. So this gave me this idea, right? Like, can I understand containers by understanding how this change root is implemented, right? It seems like an easy idea. Do you just keep peeling back the layers until you understand what's actually going on, right? Look back to first principles. So one thing I do is I find the Linux source and I start looking, because this change root, this chroot, it is a Linux syscall, right? So I can just read the code that it calls. And so as everyone I assume does in these situations, I download the whole Linux kernel and I find the code for the syscall, and it's very complex and I can't super well understand it. So I decide to go to an earlier version. It's like a trick that I always use when I find something a bit confusing, right? Software gets more complex over time. It inherits all these different parts. And so if you go back to an early version, sometimes you can understand because it's mainly just the bones back then. So I get this Linux 0.01, right? And it still has change root. It's the very earliest version of Linux I could find. And it looks fairly simple, right? Basically, you pass in a file path, and then basically it changes. You can see on line 82, it changes the current.root equal to that location, assuming that location exists and is a directory, and then returns. I mean, this kind of makes sense, but I feel like I'm missing some of the stuff. I don't really know what an inode is. So let's go back further, right? If this is in the first version of Linux, then, where did it come from? And it turns out, right, it came from Unix. This is just a standard like POSIX call, and I can find it, right? Yeah, so there's this book, Lion's Commentary on Unix, 6th edition, right? Ta-da! And it contains the full source of the Unix kernel, of the version 6 Unix kernel. And it's just printed out like this. You can actually see a lot why having 80 lines matters when you're going to print out source code, because you can fit it nicely this way horizontally. But yeah, it's literally the source of the version 6 Unix kernel, which is, from the 70s. So anyways, I go in it and it has an index. I go to the index, I try to look for change root, and it's not there. So I've gone basically back too far, but then I find that there is this guy named Diamandis Spinelli. He's a professor, and he's very interested in the history of Unix. He built a repository, a Git repository that contains the full history that he could get his hands on of Unix, going all the way back, even before this, but all the way through to today's like free BSDs or whatever. And it's in Git. And the thing is, I don't understand operating systems that well, but I do understand Git, right? So basically, I just download this repository, which is kind of massive. Yeah, I just do like some git blame type stuff until I find this, right? This is the source code for change root. So this is a commit. It was added by Ken Thompson. It was added in V7, so it's pretty close to my version number, but it was in 1979. He added this commit, which contains change dir and change root, right? Change dir is your CD. When that's the syscall you make when you're in a terminal and you change directories. Change root is the same thing, except what you're doing is instead of changing the full path, you're changing where that top slash exists, right? And you can see this very clearly with the source because change dir takes in cdir and change root only runs if you're the super user and it takes an rdir, right? And then so if you look, because I just have this in VS Code, I just click on it. There's this user struct and it has these two things, cdir and rdir. And cdir is a pointer to your current directory. It's what's returned if you type like pwd, right? And rdir is just where that root is. Like what is the pointer in the file system that is your top level thing? That's it. The change root syscall that Jerome is saying is the basis of containers is just a way to change this one pointer, right? You can already change the other pointer with cd, and this, chroot is just a way to change this other pointer. And the two of them are used together to make paths. This, I mean, maybe doesn't sound profound, but it blew my mind because operating systems seem magical and I don't really understand exactly what they do. But then here I look into it and it's just a pointer to a place in the file system. And everything else is built up on top of that, on top of these syscalls, and it blew my mind. Basically, the change root command lets you change this top slash, right? And the cd lets you change the other things, and that's it, right? So we can demonstrate basically how containers work by using this change root call to imitate what containers do. So here's the simplest Docker command I can run. I do Docker run hello world and it returns this stuff, right? It's just hello from Docker, blah, blah, blah. So we can do the same, just without even writing code, just using change root. So we can do this ourselves. We can call change root ourselves just by using the change root call in bash. So I make a new directory, make dir test root. I copy this hello program that's inside that into it, and then I can do change root test root hello. And now I'm inside that, and I started up that program, and it looks exactly the same as Docker, right? It's super simple, but this is the beginning of a container runtime. I can do the same thing in Go. So here's my little Go program. I have a command, which is the way you start a new process, right? And I'm going to execute that /hello. So I can do the same in Go, right? So I execute a command, which is that /hello. But first I do the syscall, which changes the root into that test root. And then I hook up my standard in and standard out, and I can run that, right? And when I run it like this, when I do go run chrun.go, exactly the same. I'm running this hello program, inside of a changed root, inside an isolated container to a certain extent. And you would think, okay, if this is a container, then I can do things exactly the same as I can with Docker. Like I can launch a shell inside of it and look around and it'll look like an isolated environment. But if I try that, then I just get this, no such file or directory, right? There's no way to run bin inside of this root, which sounds strange, but then if you try it with Docker, you get the exact same behavior, right? No such file or directory. So we're matching Docker so far, bug for bug, right? I mean, it's not really a bug, but so naively, the reason this doesn't work is there's no shell inside of my root, right? My container image doesn't have a shell in it, so I can't run a shell because that hello world is a from scratch container. It just exactly contains what it needs. But I can fix that, right? I can copy in a shell. So I find where my shell is, I copy it in, and then I run my new chroot, and then I still get no such file or directory. It makes no sense. And I tried the same thing using my Go program, and I get the same results as well. And that doesn't make sense because that program is there. I can see it, but if I Google it, I end up on Stack Overflow, and the person with the highest ranked answer, which isn't always right, but in this case it is, says, as mentioned by others, this is because the loader can't be found, not your executable, blah, 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 blah. And then you can see it says things about elf, da, 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 da. and you could see ld.linux, which is going to come up just briefly, right? But basically, the no such file or directory isn't referring to that shell executable, but to its dependency. That's because there is on Linux dynamic library loading, right? Yeah, on Linux there are dependencies, right? If you run ldd on this bin shell, it will give you a dependency list. And if you run ldd on those, they each might have further dependencies. Or what I like to do is this ldd tree, and it gives me a list of dependencies, right? It says this bin sh depends on lib64, ld linux, blah, 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 blah. And then that further calls libc. LD is the dynamic library loader, I believe, and libc is just the standard library for C, right? And so the problem is once we change our root into those paths like lib64 doesn't exist. All that's inside my test root is test root, right? If you look at an executable on Linux, it looks like this, right? And at the top, it has this elf header. And in there, it will say, I need to load this dependency and I need to load this dependency. And that is where things are going awry. You may think this is a weird detail of operating systems and has nothing to do with containers. It has everything to do with containers. Please stand by. Promise. By the way, like I had to quickly adapt these slides because I gave the talk a couple months ago and I felt like I might forget it. And so I just moved things around so that my head fits in. So hopefully that works. But a question that might come to mind, right, is like, okay, yeah, the C standard library, that's a pain. But what about Go? Like I'm using Go. Go can build like static executables. So maybe if I use Go, I can get around this, right? So I take my Go program from before and I do the same steps, right? I build it into an executable called chrun. I copy that into the test root. And when I run that, which I'm calling chrun, it fails, right? And you can see what I'm trying to do here actually is I'm calling chroot in my test root. And then in my test root, I'm running my chrun program, which will also create another test root and then run my hello world. I'm containering, but it doesn't matter because it doesn't work, right? It's having the same thing, no such file or directory. And if I look at what dependencies it has, you can see even with Go that with the default building, if you're doing what I'm doing and calling syscalls, then it ends up with these dependencies on libc. But if you Google this, you can find out there's ways to get around this. And so I can tell it to link things statically, and then I get no dependencies, and I can do this, right? I can do chroot, and I pass it the current directory, and I call chrun, which then will run this whole thing inside of it and run hello, containers in containers, and it works. Bam, right? So from this, I learned something, right? This isn't the full container runtime that we're going to build, but it does teach me a lot of stuff, right? That like, it's not about having a container within a container, right? It's about this tree structure, right? You have a file system tree, and you can use this change root to set a branch of it to be the new root, right? And so you can change root within change root because it's just, saying a subtree of a subtree is the new root. And similarly with containers, which we'll get to shortly. And why does all this matter? Well, because you might have statically linked stuff that you want to run in an isolated way. And this can be a handy way to do this, but it kind of breaks down when you have dynamic links, right? When you have these dynamic links, they need to be in the root as well, right? So you need to manually set them up somehow if you want to run more complicated programs. So let's do that for real, right? I want to be able to take my Redis image and start up a shell in it and look around and see that everything's working, right? Just like I can do with Docker. And when I do that with Docker, though, it raises some more important questions, right? Like, why is all of Alpine Linux inside this container, right? And how can we start something like this Redis image with our own little runtime? Well, one way that we could see what's going on is we could just look at the dynamic links for the Redis server. So when I start up Redis, it runs this Redis server program. If I run LDD tree on it, I could see it loads a whole bunch of stuff, right? Like it has that LD, it has libc, but it also has libssl, it has libcrypto, it has pthreads, and so on and so forth, right? Redis has a lot of dynamic stuff. It's loading, right? And all that stuff is inside that container. And in fact, if you look at how this Docker file is built, you'll see this giant find command here, which contains LDD and then also has this apt mark manual. And if you read through the whole Docker file, you could see like the way the Redis image is built is you start with an Alpine container and then you start installing all these dependencies so that when you start up Redis, that it will find things in the right places, right? So it's equivalent to setting up all these paths that are needed inside my new root. So everything is where it needs when it needs to start up, which explains why when we change root inside of it, we see all of an Alpine Linux in there because we need these important bits to start up our program, right? We need to have the things that are dynamically linked in the places that are expected. Also, the program might expect to load config from certain places on the Linux operating system. It might expect to write logs to certain places. People might want to shell in and poke around. And then when they shell in, they might run cat or tail or whatever. And for that to work, those need to be somewhere that they can be accessed, right? They need to be in a bin folder somewhere. And therefore, containers end up in this world where you're setting up a whole, miniature Linux ecosystem, but just the file system portion of it inside this new root that you're running things inside of. Therefore, I need to create all this myself. I need a way to take apart images and create a new root if I want to have a Docker runtime. It should be noted though, right, that there are other strategies to this. You may be familiar with Nix, the package manager slash operating system slash whatever, right? And if you go to their homepage, you will see an example where they don't have Node installed, and then they do Nix shell -p Node.js, and then all of a sudden they can run Node. And how does that work? Because Node, it has all kinds of dependencies. Well, if you run LDD on Node after installing a Nix, you'll see this at the bottom. Basically, all these LDD requirements have been installed by Nix, but into the Nix store using a hash path. And then they've modified this elf header of the Node program to tell them exactly where they are. So it's a different strategy, right? Rather than putting a whole Linux file system in a box in a container, they're doing something different and they're modifying the header and putting things in this Nix store. Different strategy, interesting one, right? But anyways, I'm not going to worry about that. What I need is to set up the file system. So one way I can do this is I can use this Docker save, right? So if I call Docker save Redis, I get a tar. If I open that tar, I just see a whole bunch of more tars, and the tars all have names, a layer.tar, and they're in a folder with this giant hash. And it turns out that that hash is the SHA-256 of the bytes in the tar, basically. So it's a content addressable store. Cool. That's how layers work. We'll get to that later, but it's not super helpful for what I need, which is the actual file system, right? So I could actually skip Docker altogether, right? I could like make curl or wget commands, grab those layers from Docker Hub, extract them one on top of the other, and build up a union file system myself. But there's an easier way, right? I can use this command called docker export. So if I call docker export and first I pass it the Redis image, then I will get this redis.tar.gz. And when I extract that using the right incantations, I get what's here on the bottom left. Like I get the full file system that's inside that Docker container, which is awesome, right? I'm getting somewhere. Then I take a look in the user local bin folder. I can see here are all my Redis startup programs. And then believe it or not, like we're getting very close to having a working Docker runtime, because what we can do, right, is we use this to pull an image tar. Then we create a temporary directory, extract all of that into it, all my Redis file systems. Then I can change root into that, start our process, right? And then on exit, I'm going to delete it. And that, for all intents and purposes, should look like the same as when I do a Docker run. And the reason it looks awful lot the same is because it's very similar, right? This is what Jerome was getting at. We'll get to that soon, though. So here's how I do it, right? For the extracting, I'll just use a simple bash script. If you pass me a thing, pull Redis, then I'm going to pull it and store it somewhere, right? Pull Redis, I'm going to pull it down. Then I'm going to extend my main method. I am going to take in an argument and look for that tar file. I will create a temporary directory of that tar. And then at the end, I will untar it all. And then in the meantime, I will run change root, right? More specifically, I do this, right? First, I create the tempter. So if you pass me the tar name like Redis latest.tar.gz, I'm going to create that folder in a tempter somewhere and give it a name that's based on that. Then I'll pass that destination directory into this untar program, which will extract it all into there. And then I'll do my change root command, which is the same from before, right? I will call the startup command, but I will do it inside this new temp directory I've created. And then just to add some ergonomics, right, I'm going to just add a switch statement to my run program so that if you run run, it's going to do this process. If you do the pull, then I'll run that pull script, right? Which means you can do chrun pull Redis down, and then chrun run Redis bin sh, and bam, you are inside of a container that's using arch-chroot, and you can see everything's in there. It looks the same as if you did a Docker run. That is a working container runtime. And so the way you could demonstrate that is I do chrun run Redis, and I pass it the Redis startup command, and then I have a running container. And you can see the path here in /temp assets Redis tar. And then once that's running, I can open a new tab, right? And I can start up the CLI. And then in that CLI, I can do Redis things, right? I can set this key, hello world, I can get this key, I can kill this container, start up another one, read those keys in there, etc. It's all working container stuff. So you can find the code for this if you wanted to use it. It's online, change root containers. I should tell you, you shouldn't use this, right? This is a very limited container runtime. There's some things missing that we'll get to shortly, but it is there. You can use it. It will only work on Linux right now. But yeah, check it out. But the important point is not that container runtime, right? That doesn't matter to me that much. It's more what you learn along the way, right? The running container is just a process, right? When you run a container, it's just a process running on the host machine. It's not really like a VM at all. It's just starting up a process that has a different, more restricted view of a part of the file system, right? It's a process that has a different, file system attached to it that has a different, Linux file system there. And we need all that because that's a way to make dynamic linking work, right? And there's some other reasons, but that's a big reason, right? It is a way to package up a whole Linux file system so that you can run a program without having to worry about dynamic links. Now, there are other things that make containers work, right? There's some things that are missing from this. So let's talk about those. But yeah, here's the big takeaway, right? Let's see what this container is. A running container is just a process. Oh yeah, before we get to the extra things to add to make this a real container, what about Earthly, right? I think this explains the Earthly story well. The reason that Earthly is using containers for specific build steps is containers have very little overhead, and they're a great way to get isolation. So if you're building some complex software and you can split things up so that the various build steps are isolated from each other, then there can't be like interdependencies that haven't been explicitly declared, which give you a very repeatable build, right? And then Earthly can use this structure to build like a graph of how your builds work and what the inputs and outputs are. And based on that, it has the type of information that a really fast build system like Bazel has. And it can do cool things like build things more parallel, right? It can do your CI process faster because it understands the explicit dependencies between steps. Or it can cache specific steps because it knows exactly what the inputs into them are, right? And so the important thing isn't boxes within boxes. It's that if you break your build up into specific steps and you know the inputs and outputs of them, then you can intuit from the outside ways to make it faster and ways to cache it. And you can get really cool speed ups in your build process and also just simplifications, right? So yeah, this is my commercial for Earthly, right? I work for Earthly. I'm making this video here on Company Time. Check it out. It's pretty awesome. But yeah, if we want to make this real, one thing we need to do is add namespaces, right? Namespaces, Linux namespaces they're basically the same as namespaces in a programming language, right? If I have a global variable, everybody can see it. But if I have separate namespaces, then I can create a variable with the same name in two separate namespaces because they don't see each other. They're separated by a namespace. Namespaces are just a way to give like a unique view of a global resource, right? It's about what you can see, restricting what you can see, right? There's a whole bunch of different namespaces There is the network namespace, the mount namespace, which is like what file systems are mounted, the PID namespace, which is process IDs, and the user UIDs, etc. So one thing that I didn't show you is that if you were to run PS inside of that container we started up, you would see all the things running on the host machine. Reason one is because you are on the host machine, but the reason why it's different than Docker is that Docker is running inside of a separate PID namespace. And so you only see your processes, you don't see anybody else's. Same for users, right? The users are the same in mine because we're in the same user namespace. But if you set up a different user namespace, then things will look different. You'll get different usernames. UTS, which I think is Unix time system, is the very first namespace that was created, I think, and lets you set the host name. So right now, the way we set things up, the host names are the same. We're not setting up a new namespace at all. So the visibility aspects of a container that make it seem like it's an isolated environment aren't there. That can have some advantages, right? The network namespace we didn't set up. And because of that, it was easy for these two things we started up to talk to each other because they were on the same local network, right? I didn't have to map any ports or anything, and that's because of the network namespace not being set up. So you could set these up using unshare, right? You're unsharing global resources. It's a bit of a weird way to phrase it, but it kind of makes sense. So if we wanted to make our container, more robust, if we thought, hey, Kubernetes should use chrun, they're going to be like, yeah, you need namespaces. And in fact, when I was building all this and I was watching more talks, I found this great talk by Liz Rice, and she does something similar, builds a container runtime. Although it can't start things from Docker Hub, it does have namespaces, and she spends a lot of time explaining how they work, and it's really great. And so this at the bottom here is just some code from her runtime, which will set up the namespaces. So you could add that to the code we have so far, and now you'd have namespaces. You can see that she is using clone and unshare to set up the different namespaces, right? New UTS namespace so that you can have a different host name, new PID namespace so that the processes lists are isolated, etc. So add this code from Liz and you're all set. Liz's talk is awesome, by the way. You should check it out. In it, she live codes the whole thing. I originally gave what I'm showing you here at a conference and I wanted to live code it, and it turned out that I'm just not good at like typing out code and talking at the same time. I'm struggling just with the talking part. So she's good at what she does. The other thing that you might want to add though is cgroups. Cgroups are control groups, and they're a fairly new Linux feature that allows you to put restrictions on the container. So you can do things like set memory limits. If you've ever had the ohm killer out of memory, Linux kernel kills you. That's for memory limits. You can have IO limits. You can have CPU limits. You can set process prioritization, right? So if you've ever done a Docker run and set memory equal to 10 megabytes, or if you've messed around with Kubernetes trying to give more memory to your pod so that things are getting killed, this is using cgroup. And so you can set cgroups in a number of ways, but the more interesting way is this virtual file system call. So you basically like write pretend files into sysfs cgroup to configure cgroups. And if you want to set up cgroups, again, stealing the code from Liz, here is some to set up a PID's max cgroup. So she basically demonstrates in her talk, hey, you can set up this cgroup so that my process can only start up a maximum number of sub-processes, right? PID max. So in that namespace, there are only allowed to be 20 processes. You create it 21st, kernel's gonna kill it. Pretty cool. We could add that code. We could add memory limits. We could add whatever cgroups we want and make this a more real world container runtime. The other thing that we would want to add to make this more real is use pivot root. So change root, chroot, it's been around forever. It goes all the way back to Unix, early Unix. But there is ways that you can escape from that root if you can get a reference to outside of it. And so pivot root is a more modern version. I don't totally understand what the differences are, but I believe it unmounts where you came from, so you can't get back. The other thing you might want to do to make this more real is less to do with its behavior and more to do with making it faster. The way we're doing it now, each time you run a container, it's untarring that whole thing, and then at the end, it's destroying it. So you get the behavior of a container where changes you make aren't left behind. But it's a bit slow to create this all the time, right? And if you have a bunch of containers and they all share a certain version of Alpine Linux, Like there's no sharing going on there. Each one is just this giant tar. So layers let us separate this out. We can share layers across images. And the union file system is a way that these are mounted read-only, one on top of each other, each layer, and you only write into the top. And makes it a lot faster to start these things up. So that doesn't affect behavior so much as just making it fast, which I suppose is a behavior. But a nice thing about this project is it lets you see why things like this make sense, right? Because you can see that, oh, if I have a giant 20 gigabyte container, then doing this every time is going to be slow. So if I can split it into layers, you can see it would be a lot faster. And if I can share layers across things, it makes sense. And that's where they ended up. But all this brings me back around, right? So like, what is a container, right? So back to this original talk, Jerome Pedizzoni says, a container feels like a VM, but it's just a normal process. It's just a process running on your host machine. That's it. And this helps explain a lot, right? When you have questions about containers, if you think of them as just a process running on a Linux machine, then you can answer a lot of questions, right? Why are containers slow on Macs and on Windows, right? Well, because these are all Linux features to run these containers on your Mac or on your Windows machine. You're actually running a virtual machine that's being a little bit hidden from you. And inside of that, it's just a process. But if file transfers are slow, it's not actually to do with the slowness of, the container interface. It's to do with just transferring files between a VM, has overhead, right? Why does my Docker container take a while to start, right? Well, like in its simplest form, like a from scratch Docker image is just a process being started up, right? So if it's slow, I mean, maybe it's a giant container with a lot of baggage, or maybe your program's just slow to start up. Like it's nothing necessarily to do with the containerization, right? What's the overhead of something being in a container in Kubernetes? Well, it's nothing, right? All that's happening is it's getting a different view of things and it has these C groups restrictions. There's not really a lot of overhead besides that. But it's awesome that by building something simple like this, you can kind of understand all that and be able to reason about some of these questions by just reducing it to a simpler question, which is what, is the overhead of being a process. Yeah, so that's my talk. Thank you. Check out Earthly. Like and subscribe. Am I supposed to say that? Yeah, I'm Adam Gordon Bell. Check out earthly.dev if you want fast builds that use containers. You can find this code on GitHub, but yeah, probably don't use it. That's a bad idea. And if you want to know about me, just Google for Adam Gordon Bell. Thank you very much.